Hi, this is Ms. Shank, and this is for continued honors chemistry notes for the gas laws. So we've been talking about gases and the behavior of gases. Some reasons why we might think about the behavior of gases is for things like hot air balloons, like what makes them get lifted up and how can they get back down when we need them to. Checking the pressure in your tires. That's something that's really important to all of us, and we know that in the winter when it gets cold we have to think about our tires might get a little smaller, or in the summer when it gets hot they might expand a bit because of gas pressure. Also, a fire extinguisher uses the concepts of gas pressure to be able to properly expel what it needs to put out a fire. So we've already talked about a couple of the laws. The first one we talked about was Boyle's Law, and in Boyle's Law we talked about the relationship between pressure and volume. So the less volume that these are in, you can see that the pressure is going to be higher. It all has to do with collisions, so the more compressed it is, the more collisions those particles are going to make, and the higher the pressure is going to be. We also talked about Charles' Law. And in Charles' Law, we talked about how if you increase the temperature that those gas particles have, then they're going to also increase the volume. So today we're going to talk about a new law. The new law is called Gay-Lussac's Law. And Gay-Lussac's Law has to do with the direct proportion relationship between temperature and pressure. So if you lower the temperature, those particles are going to move less quickly. They're not going to collide as often, so the pressure will be less. If you heat it up, those particles are going to move faster, and of course if they're moving faster, they're going to run into each other more often. So the definition for Gay-Lussac's Law: when volume is constant, the pressure of a gas is directly proportional to its Kelvin temperature. Again, we do use Kelvin because there are no negative numbers, and because it is a directly proportional relationship, we're using division. P1 over T1 equals P2 over T2. Of course, this is going to have the same graph for directly proportional relationships as you saw before. So temperature and pressure, since it's a directly proportional relationship, we'll see a straight line. Okay, so we're going to do some examples. The gas left in a used aerosol can is at a pressure of 103 kilopascals at 25 degrees Celsius. If this can is thrown into a fire, what is the pressure of the gas when its temperature reaches 928 degrees Celsius? I suggest you pause and underline what components you have and label them. So you should have labeled P1 and T1, and T2 is right here, and we're finding P2. Thinking about units, the one that has to be really consistent is we always have to use Kelvin for temperature. So I'm going to add 273 to each of those temperatures, and 25 plus 273 will give us 298. 928 plus 273 gives us 1201 Kelvin. So we have to use those Kelvin temperatures. I'm going to plug in P1, 103. It doesn't really matter if I'm using kilopascals or another unit, just as long as I'm using the same unit for both P1 and P2. My T1 is 298. P2 is my unknown, so I just leave it as a variable over my T2, which is 1201. The easiest way to solve is to cross multiply. So we're going to do 103 times 1201 equals 298 times P2. I suggest that you pause and try to calculate it for yourself. Make sure that you're able to. Also think about what unit you would use. So as we divide both sides by 298, we should end up with 415. Again, the pressure unit doesn't always have to be the same for every problem, but within a problem, we need to have the same unit. In this case, it was kilopascals. So that's 415 kilopascals. Significant figures, I had 3 sig figs, 3 sig figs, and 4 sig figs. So 3 was the lower number, so in my answer I will go ahead and just stick with 3 sig figs. That's the multiplication and division rule. The other law that we want to talk about today is the combined gas law. This combines the 3 that we've talked about, Boyle's, Charles, and Gay-Lussac's laws. If pressure, volume, and Kelvin temperature are changing, they do so that the ratio of the product of pressure and volume over temperature is a constant. So we're just going to combine those other 3 laws. P and V were multiplied, and each of them had been divided by T. So we're just going to put it all together. P1 times V1 over T1 equals P2 times V2 over T2. When we do our example, we're looking for all 3 of those, P, V, and T. Go ahead and pause and underline what you think P1, V1, T1, P2, V2, and T2 are. So V1, T1, P1 were pretty easy to find. Did you find the others? Well, V2 is what we're finding. STP, remember that? STP is standard temperature pressure. Standard temperature is 0 degrees Celsius. Of course, that's 273 Kelvin. Do you remember what standard pressure was? 1 atmosphere, but I have P1 in kilopascal, so I can't just use 1 atmosphere. That's 101.3 kilopascals. Now that we have all our components, all we have to do is plug in our numbers. So P1 was 153 times V1 was 30.0 over T1, which I'm adding 273 to get 313. And that's equal to P2, the 101.3, times V2, which is my variable unknown, over T2, which is 273. Again, try to solve it before you look. So cross multiplying, I've got the 153 times 30 times 273 equals 313 times 101.3 times V2. I went ahead and put a division here of 313 times 101.3 on both sides, and I got V2 equals 39.5 liters. I used 3 significant figures because if I look at all these measurements, they're all either 3 or 4 sig figs, so I'm going with the lower amount, which is 3.